So last time I went on this big rant about how we don't need to know the index of things, and then immediately later we found out apparently we did want to know the index of things. And the question was asked, like, well, why index of and why find? Well, find will have as this internal private one, and it returns a sentinel value, but we're going to have this public-facing one where it's going to not return a sentinel value, but it'll just throw an exception if something funny happens, if the thing you look for isn't there. So what we're saying basically is the proper use of this is, if it doesn't exist, don't call index of. Like, you should never be calling the index of something that never exists. And if you do, that means something weird happened. And if you're wondering, well, why would I design it that way? Because I wanted to. Remember, when we're writing this code, we are the inventors. We can do whatever we want. It's up to us. So there's the index of. And all index of does is calls find, which if we go up here, here's find. It iterates through, checks if we find it. It's just a linear search. If we find it, we return the index. If we don't, we return not found, which is just -1. And then contains just checks, well, call find and let us know if we found not found or not. So if it's not there, throw the exception. Otherwise, just return the result of find. So this is a wrapper method. It's a public-facing wrapper method that calls the private one inside. You have a question?
Wouldn't like creating a find index of method that when it's not found assign the -1 value? If we reuse it, wouldn't like the -1 be assigned to the last object?
I'm not quite sure what you mean.
If we create a code where you want to find the index of something and do something with that object, wouldn't like calling the find if it's not found, wouldn't like the value
Oh,
-1?
I see what you mean. So the answer is no, because you're thinking Python. And in Python, when you index a list with -1, it's syntactic sugar for length -1. In Java, that's not a thing. In most languages, it's not a thing. If that was a concern, like in Python, using the sentinel value of -1, you're right, could create an issue. But then, like if I'm the designer of the code in Python and I return -1 because it's a sentinel value, then we would know that, like, okay, proper use of this is -1 means not found. And if you are using it such that you're using the not found to index the last element, you're misusing this code. Now, it's always important to design your code to eliminate that type of stuff. But in Python, it's a little bit more tricky. In Java, it's a lot easier to have much better control of your code to make sure it's used the right way. But interesting question, yeah. Should we clarify? His question was, well, if you return not found, which is -1, that means like the last index in Python. Yes and no, right? It really all depends on what do we want it to mean. But anyways, the method checks if findings. Yeah, okay. Get. Now here we've got a get method. This is kind of like indexing an array, except we have to do it through a get, right? Because we don't have an array. We have a contact list object, and if I want to index a contact list, I can't index it with the square brackets. I have to index it with something else. And we use this method get. And what get's going to do is it's going to return the friend object or a reference to the friend object at some specified index. But we've got some like bounds checking here that basically says, well, if you try to index with something less than 0, or if you try to index something that's greater than equal to the size, you're out of bounds. In fact, we can raise a index out of bounds exception. That's a built-in exception in Java. There's no question on the test type thing that's going to be like the trivia of what are all the included exceptions in Java. No, you just find the one that makes sense for your needs. You'd be like, so I want to, okay, if they give me an index that doesn't exist, I type into Google, what exception is good for this? And then this would be like, use this. This is what this is for, right? In general, you're looking for like runtime exceptions, but you try to get more specific. More on exceptions later, not overly important right now. If you try to index an array at like something that doesn't exist, this is the exception that Java gives you. Like it'll throw this exception if you try to index an array at an index that doesn't exist. And the message I'm giving to the exception is, well, the index. So it'll be like index out of bounds exception, and whatever I put in here, that would get displayed. In the same way where if I had, let me show you. We'll let it do its thing. But yeah, exceptions are objects. You create an object. That's why you see like new, name of the exception. New, index out of bounds. So this is an object. And we give it an argument. The argument is its message. And you put in whatever makes sense there. What? Have I really never... What? There must have been an update or something. Interesting. So let's create some, I'm just going to make an array. Int array, my array equals a new int of size 10. Whoops. Thanks, autocomplete. And then s out. My array at index -1. Well, first of all, it's going to be like, well, this isn't going to work. But that's just a warning. When we try to run it, what's going to happen? We're going to see Java calling this, trying to index an array at an index that doesn't exist. We get back array index out of bounds, index -1 out of bounds for length 10. Right? That's its message. Pretty good message. For us, our message, we were lazy. We just included the index that it was. I didn't say index -1. I could have made like a string. Index -1 plus index plus is out of bounds for array length, array.length. I could have made a bigger message, but I kept it simple here. So if it's not a valid index, if it's less than this, or if it's greater than that, raise the exception because you can't index a list outside of its range. Otherwise, return the friend at some specified index. Pretty straightforward stuff. By the way, I realize you're all done the assignment now, so this should really be review, but we're doing it anyways, just in case questions come up. A remove. Now, this one's interesting because we have a couple of options here. So first, if we try to remove a friend, if it doesn't exist, do nothing, return false. Right? Remember how add returns a Boolean that tells you like true, false, whether or not it was successful or not? Remove is similar. It returns a Boolean, true, false, whether or not it was successful. If it doesn't exist, return false. You might say, why not raise an exception? We could do it that way if we wanted. You're absolutely right. There's nothing wrong with doing it that way. But I'm designing my remove to align with the standard, like the Java standard libraries collection add and remove, they return Booleans on the status of whether it was successful or not. So if you try to remove something that doesn't exist, just return false, whatever, it didn't work. Otherwise, what do? We find where it is by calling the find method. Now, here's what we do. Imagine I have an array. Actually, let's see, do I have a picture here? I might just have a picture. Yes. This is what I'm doing. All right? Where this is the one I want to remove. But what I'm going to do is I'm going to say, well, okay, look. All I need to do, in order to like remove something, all I need is to remove reference to it. Okay? If Java doesn't have reference to it anymore, it's as good as gone. So this reference variable in the array, we'll have it reference the last thing. And then we'll set the last thing to reference null. Now, you might say, do we really need to reference null? It kind of depends on certain situations. If we know that this references this guy, but we know the length is really 1, 2, 3, 4, the thing at index 5 doesn't really exist, even though it references. But it's always kind of, that could backfire, by the way. But in general, it's always safer to have your code do what you want it to do. So it's always nice to be like, and have this set to null. I'll show you what I mean in a second about that. But here's the idea. You remove this reference by updating it to reference the last thing. Now, let's make this bigger. If we have like A, B, C, D, E, F, okay, let's say. These aren't references now. I'm representing the contents of A, B, C, D, E, F. They could be references. They could be integers. It doesn't matter. But what I'm effectively saying is, if I want to remove B, what I do is I take whatever's in B and I just copy over what's actually at the end, F, like that. And then I go to the end and I set this to be just null, right? I'll just a dash to be null. So now it's not there anymore. Great. But what do you notice?
It's out of order.
It's out of order. That means that there must have been like, there is clearly an ordering. There was clearly an ordering. But that begs the question, did order matter? So, let me put it this way. The alternative could have been, move this down. Move this down. Move that down. Move that down. Set this to null, whatever. Or move whatever, right? Move everything down. There was 1, 2, 3, 4 things behind it. How many things did I have to shuffle? It's not a trick question. 4. If there was 100, how many things would I have to shuffle? 99. Sure, find edge cases, whatever. But let's, for simplicity, let's say 100. There were 100 after. I got to move 100 down, let's say. If there was 1 billion, how many would I have to move? If there was n, how many would I have to move? N. Right? The amount of work I need to do depends, am I recording? Good. Depends on how many things are there. If I shuffle it all down, but that's not what we did. We didn't do that. All right, A, B, I made this F, A, B, C, D, E, and we set that to null. Let's go back to this case and think how many steps. It's always nice when you can kind of like write a letter without having to write the letter, yeah. How many steps is this? Like, well, let's call it 2, because I know it looks like 4, but I can overwrite in one step and then overwrite in another step. I know it did look like 4, where you removed and then you put in. But let's call it 2, let's call it 4, whatever. It took like not 100. How many things were there though? 4. And it took like, let's call it 2 steps. What if there was 100 things? How many steps would that take? 2. What about 1 billion? 2. What about n? 2. The amount of work did not depend. The amount of work was constant. So, if you are given 2 potential solutions to a problem being, I've got a gap. I want to get rid of that gap. We want to fill that gap. 2 solutions. Shuffle everything down. That takes linear time. Or just put the last thing in there. That takes constant time. What do you want to do? Well, if your goal is to minimize computing resources, obviously you take the constant time one. That's obviously the better decision. However, if the order matters, that ain't going to work. If it's important that these stayed like alphabetical, for example, I can't just put an F in there. That would destroy the ordering. If the ordering is important, I'm kind of stuck with that linear operation. If it's not, then I can cheese it and do it in constant time. It all depends on what do we need. So when the question is what's better, it depends. It's not far into computer science. You're in 162. We're at the beginning of 162, where your solutions are always like, it depends. You now have choices to make. And the right choice might not be obvious. Maybe it is, but you have choices. Now, what I was saying, like, well, do I really need to set this to null? Here's why I was asking that question. Is you could say, like, look at this code here. I decreased the size. So before, the size was 1, 2, 3, 4, 5, 6, right? The size was 6, right? But if I did this, where I put the f here, and I leave this alone, and then I just say, well, the size is now 5, and you're like, but there's 6 things in there. Yeah, but I don't care about that last thing. And if I go add a new thing, it goes here. It'll immediately overwrite what's there. So even though the f still exists, we can pretend it doesn't. Now, why delete it then, right? Because like, well, if I'm going out of my way to do extra work to delete it, first of all, it's constant time. Now you might say, what if I have to do the constant time thing a billion times? That's going to add up. You're right. You're absolutely right. But that type of optimizing maybe depend on your compiler to figure out. When you write the code, I find this code very descriptive. Update it, set that last thing to be nothing. It's gone. Someone looking at this code, they knows what's going on. They know what this is doing. The intention is very clear. And further, if the data shouldn't be there, don't have the data there. Does it really matter that it's there? It doesn't seem like it, but get rid of it. If it's not supposed to be there, get rid of it. It's better. Okay? Cool. Was that clear, though, about how, like, we could leave it? Functionally, it seems safe. Yeah?
So essentially, don't leave it there so that could potentially cause a problem at any point.
Well, maybe it could cause a problem, but also your code, the functionality that you want your code to like communicate to a human is clearer this way. Move that last thing down, set the thing at the end to null. Right? Yeah.
Is there a way to, instead of doing that, like if we remove B, we just tell Java to ignore that index and just go to the next?
You could, but that's going to create a lot of bookkeeping, and that's going to be a pain in the butt. Well, because then you would need to be like, but this index doesn't exist. Where you're going to keep track of all those indices that doesn't exist. You want to do it? Be my guest. Don't do it. Don't go to your way to make a more complex solution. Which is, I know it's always fun. Could we do it this way? Maybe, probably. Should you? Yeah. He was saying, could you like mark this one as like non-existent and then we just skip it in the future? Well, yeah, you could, but then you'd need a way to keep track of what was marked non-existent. And you could do that. How are we going to do that? Well, let's make another array. Let's make it a Boolean array. And then every time we could just go through the Boolean and then check. Or let's just, update the array, right? You could do it. But maybe you shouldn't. It's up to you. Maybe for whatever reason, because remember, what solution is best for you? Maybe that is a good solution for your particular situation. For this one, nah, let's keep it simple. Okay. If it does not exist, an exception will be thrown. Okay, first, remove first checks if friend exists in the contents. If it does not, an exception will be thrown. If a string, wait, no, it doesn't. This must have been, I must have changed this and never updated the text here. First check if it does not exist, an exception will be thrown. Nope, it returns false. That's an old version. A string representing a product friend is given an exception. Okay, that's old. That needs to be fixed. To actually remove the friend, all that needs to happen is for the program to lose reference to it. In the above example, the array, okay, this is just explaining what we already did. We set it to null. Although not necessary, it's a bad idea it's not a bad idea to explicitly remove the reference at the end, and this is what we're doing. Cool. Clear. So we have a couple of options to clear. One is to go through our array and just set everything to null, right? We could do that. We absolutely could do that. Or we could just kind of cheese it and just make a new array and set the friends field to the new array. Right? Why might you want to do this? Well, imagine I have a friends array of size 1 billion. I have to go through 1 billion things and set them to null. So if I have like friends, referencing that, I go through, if it's size n, I got to go through all n things and set them to null. Or I just make a new array of however big I want and then just, update that. There. Easy peasy. A little easier. Both would work, but, a little easier. If you're really worried about space and where that array was saved in RAM, yeah, sure, maybe you can go and clear out the contents of the already existing one, but this would work just fine. Here, simply create a new array and set the size to 0. That would also be important, of course. The garbage collector will come along and eventually delete all this crap anyways. In a similar way that like when we did expand capacity, it would delete the old array. It would collect and remove the old array. But we never lost the contents because we kept reference to it when we were doing expand capacity. Remember we copied over the reference? So that was fine, but the array itself would get removed. And that's an important thing to note, by the way. If you have something like an array that references something, right? But if we have no reference to this, you might say to yourself, well, but this references something, so it's important. If I can't reference this, it's as good as gone. And if nothing else references this, and we need that, we're in trouble. Or maybe it's a case like I'm clearing and whatever, I delete reference to this and then this gets removed too. Does that make sense? Yeah. If you have a thing to a reference that references something that references something that references something that references something forever, 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 and I lose that first reference, everything's gone. ToString. Now this is a fun one. A good representation of a collection would be an aggregate of the strings of the things in the collection. You know how like when you print out a list in Python, you see like index 0, comma, index 1, comma, index 2, all the things in that list, right? That's how it shows it to you. We could do something similar. Okay, a good representation, okay, so what we'll do is we'll just, if we have like a list of 5 friends, we'll just take the string representation of each friend and then print them out. Now, I'm not going to put them all on one line. For nice formatting reasons, I'm going to go like one friend, new line, another friend, new line, another friend, and so on. And we'll have something that looks kind of like, oh, I don't have the example here, but that's fine. All right, now, there is a bit of an issue here, though. And this issue existed in Python too, but it's really obvious in Java, but there's a nice workaround for it. Strings are immutable. So when you do string building, if I make a string and then I concatenate to that string, I'm not concatenating to a string. What I'm doing is I'm making a new string based on the old string and the one you want to concatenate to it. So I'm never modifying the original string. I'm creating a new string. And if I've got a list of like 1 billion things, that's a lot of objects being created. So instead, what we do is we use something called a string builder object. And a string builder, you can kind of think of it as like a list almost, where you make a list of individual strings. And then when you're done, you concatenate them all together, instead of making like the bajillion updated strings as you go. This is a little bit nicer to the computer computationally. So what we do is ToString returns a string. String builder, I called it builder. It's a new string builder object. Then for I from 0 to size, and remember it's to size, not to the length of the array, because the array might be length 1 billion, but you only have 4 things in it, and we only want to iterate to 4. Builder.append, friends at index I, and then builder.append a new line. And then when we're finally done, you take the builder and you call its ToString, which then takes all the individual strings and makes one big string in the end. It's a little nicer for your computer. Saves oomph. Any questions about that ToString? It's cool because now you're like, wait, how did this, remember, when I do with the append here, I didn't write it, but You don't need to explicitly say, hey, friends at I dot toString, because this will automatically turn this into a string. In the same way that, like, if I print out a friend object, I don't need to call toString. The system.out.println will call the toString automatically. But this takes the string version of the string representation of a friend and appends it to this, and then, I mean, it calls the builder's toString in the end too for this toString. Happy, sad? Questions, thoughts, concerns? Okay. In the above, okay, the instance of friend object is not, are not having their toString method called explicitly. This is unnecessary since the string builder's object append method would call it automatically. And then equals in hash code. Well, here we go. Here, I've combined two of the checks. Remember how I did, like, is it the same thing? Is it null? Well, here I'm doing null or this, so I'm doing both at the same time, just for simplicity. Otherwise, contact list that. I cast it, O, as the contact list. And then really what I want to do is just check if the contents of the arrays are equal. Here, order matters, because if it didn't, it would say that these friends lists aren't the same, which is interesting, because should the contact lists, if I have friend A followed by friend B, and another contact list has friend B followed by friend A, are they equal? I don't know. Maybe. That's up for us to decide. Do you see my point? You might say, well, they're equal. The order doesn't matter. Okay, we could do it that way. Fine. Or we could say, no, in order for them to be equal, their contents need to be the same, and the order in which the contents exist need to be the same. That's how we'll define it. And that's what we're doing here. But if you feel really strongly like, well, we could implement it that way, you could. But again, this is our decision. Yeah?
What does the 0 do?
The 0.
In the return?
In the return? You mean like down here?
Yeah.
That's just in the arrays.equal. So arrays is a class full of static methods for arrays. And there exists an equals method within it. That's a very quick and dirty way to check if the contents of arrays are equal. Now, what I could do is I could set up a for loop. I don't need to use arrays.equal. All this is doing is like setting up a for loop and starting at 0 to length and saying, are you two the same? Are you two the same? Are you two the same? If any of them aren't the same, it returns false. If it ever finishes, it returns true. That's all this is doing. In fact, arrays.equals, what's going on here? How do I, what's going on?
I mean, you're not logged in.
Is that the problem? Why
So
not?
it could be.
I got an update too.
And did it ruin everything for you?
I didn't check.
You didn't check.
You're not on the community version, but you can see you actually.
Yeah, but I've definitely logged in.
Yeah. I mean, it said you weren't, so you must have just decided to log you in for no reason. Because you
Let's try again. All right, well, I'll figure that out. Okay, let's see, log in. Great, yeah, this is perfect timing for this. I don't know if is this gonna work? Hey!
theoretically, anyway. Oh, yeah.
You can close this page and return to the IDE. Are you sure?
Yeah, it says your name now, but it's also still complaining. Oh, okay, cool.
All right.
Because it needed you to click that button for some reason.
All right, cool. All right, so anyways, like I was saying, arrays dot equals. Now it's going to be mad because I don't have, okay, first of all, yes, okay, import, yeah. And now it's going to be mad because it needs several things. There. So first of all, it's null safe, which is nice. It checks, okay, are you guys null? Great, okay, whatever. Then it checks, are their lengths the same? If they're not the same, they're not equal. Although, this could be an issue, by the way, because, well, what if So this might actually be an issue. But the way I'm using it, it should be safe because I'm specifying int from index to index. Yes. And their lengths need to actually be the same. Okay, cool. This is good. This is good. This is good. If I have two arrays, remember, the lengths of the arrays don't really matter. If I have like A, B, what's in the contact list is A and B. The size of the underlying container doesn't actually, it shouldn't matter. So we have to make sure we're using like the right version. And the version we're using is the one that takes, there's a lot of overloaded versions of arrays.equals. And the one we're using back here is the one that takes the array, a starting index for that array, and an ending index for that array. Another array, the starting index for that array, and an ending index for that array. Now you might say, well, it's 0 to size, 0 to size. Yes, but it's possible to check like different segments of arrays to check if they're equal. So we could do something like that. And in fact, we will do something like that in the future. But for now, I'm saying, okay, check that between this index and that index, the contents of the arrays are equal. And the one we were using was checking, well, is the difference between the difference between these two values equal? If they're not equal. Meaning, if I had something like this, it would say, well, the size of this array that I care about is 2, but the size of this is 3. Are they equal? There's no way. If one has 2 things in it and the other has 3, they're not equal. But their capacities, but like the inverse doesn't necessarily need to be the case. The size I care about is 2, but their capacities, this one's capacity might be 3 and this one's capacity might be like 6. That doesn't matter. Anyways, we're using arrays.equal. If you're like, wait, what? I don't like that. Then you, by all means, go ahead and write something like this dot size. Now this won't work because it's not implemented in anything, but I could be like this dot friends at I equals that dot friends at I, and like so on and so on. Like I could do a for loop where I check each one, but calling arrays.equals, well now it's doing this like mismatch. What's this? And now it's doing, I don't even know, vectorized mismatch. Oh, it's some weird, freaky Java syntax, but it's still a for loop iterating over the contents of those array with wrapper over wrapper over wrapper. But the spirit of what it's doing is the same. Compare each pair and check that they're equal. By the way, what I just did here, very bad. I shouldn't do this. I'm checking sameness. I shouldn't do that. I should say equals. In fact, this could be even better. What could I do instead of saying my friend.equals another friend? Who could tell me? Objects.equals, because it's the null safe version, right? All right, so there's the equals, and then the hash code. A lot of ways you could do this. Like I'd said before, not overly important for you to have a very firm understanding of what's going on here. Remember that with the spirit of the hash code, if 2 things are equal, they should have the same hash code. If they're unequal, they should have different hash codes. But collisions are inevitable, meaning if 2 things are unequal, it's possible that they have the same hash code. Anyways. And if you're like, how do you know that? It's pretty easy. I can represent a finite number of integers, right? Because I have a limited number of bits in my computer, so there is a finite number of integers I can represent in my computer. Okay? But I can represent an infinite variety of student objects. So by like the pigeonhole principle, you can't It won't. Who here knows what the pigeonhole principle is? Okay, let me put it this way. Here's the pigeonhole principle. This is a good thing to think about. It's really obvious, but giving it a name is a good thing. I have 9 holes for pigeons. Okay? But I have 10 pigeons. And I gotta put them in those pigeonholes. And there's 10 of them. That means at least one of those pigeonholes will have at least 2 pigeons in it. Why? I could put all 10 in one of these. That's one extreme. The other extreme is I put them all in each. I still have 1 pigeon left. Where do I put it? So if I have an infinite number of pigeons, but a finite space, I'm going to have a collision. It's going to happen. Right? Now, we got a lot of different, there's a lot of actual pigeonholes when it comes to hashing, but there is a finite number. Yeah?
Is there like a code equivalent of like taking a feather out of the last pigeon and then putting the pigeon in one box and then the feather in the other one so it has a unique ID?
I don't understand.
Okay. I mean, like, if you divide the last pigeon so that it has like
Pigeons come in discrete units. You cannot, they are atomic. You cannot divide pigeons in this particular situation. Stop trying to win the analogy.
Like a reference?
Pardon?
Like a reference?
Like a reference? No, he's just being silly. He's like, well, what if you cut a pigeon in half and such that you've distributed across? No, we're leaving those poor pigeons alone. All right, so how do we do their hash code for situations like this? Well, here's a common pattern. You hash the size, and then you take the result, you multiply it by a prime number. Why that prime? Magic reasons. And then you add the hash code of each individual friend to it, and then you take that, and then you multiply it by the same prime, and then you just keep doing it. That's the magic way we're going to do hash code for collections like this. No further questions on this. All right. Okay, yada, yada, yada. 97 is used to scale the result since it's a nice prime. It increases the chance of producing unique hash values because it's magic. Warning, the contact list test class is provided below, meaning you can download it and play around with it. I would recommend that you do. It's contact list test. Look at it. But I'm not going to cover it here. Testing collections is very difficult for a variety of reasons. The first collection that testing will be covered will be the array stack. Array stack is a simpler collection than this. Now, we did start with a relatively complex collection and how we want to interact with it, but we're going to go down to a simpler one and then really start thinking about the properties of these collections as we go and add more to it and see what we do. You'll notice that computer scientists are always obsessed with what constrained world can I create, but what can I do with it? And then if I modify my constrained world just a little bit, what can I do now? And so on and so on and so on. We love that crap. And hopefully you do too. You'll make a good computer scientist if you do. Anyways, any questions about any of that? If you finished assignment 1, this review should have been review. Look, if you finished 161, this review should have been review, just in Java, right? But the same ideas are the same from Python. All right, you ready to actually start the course? Welcome to 162. Now that we've done review for 3+ weeks, we can start 162. Collections in abstract data types. What are they? Well, a collection is a group of things that are treated as a special conceptual unit, like a contact list or a collection of stamps or a country catalog, whatever. In computer science, there are a few popular elementary collections that we play with. Stacks, queues, bags, lists, trees, and graphs. There's a lot more, and there's a lot of variations of these things, but we're starting here. And then we're going to go to here, and then we're going to go to here. These kind of smush together. And we're going to talk a little bit about trees. We're not going to get that far into trees, but we are going to talk about trees. And we're not going to talk about graphs, although I totally make you use graphs, but you don't realize it, but that's another thing. This list is obviously far from complete, but they will be a big part of your, like, this semester and 255 if you take 255. Who here thinks they'll take 255? That's like what comes after this. Perfect. It's a great class. Way better than this one. All right, linear collections. So linear collections are those that arrange the data in a nice sequential way. There's a beginning, there's an end, assuming it exists. If nothing, you can have a linear collection with nothing in it, fine, whatever. Everything has like a predecessor and everything has a successor except the ends, right? The thing at the beginning doesn't have a predecessor, fine. And the thing at the end doesn't have something that comes after it. But otherwise, there's a line. If I gave you an array and pointed to index I and said what comes after it, you'd be like I plus 1. If I said what comes before it, I minus 1. You know where it is. You could draw a nice straight line connecting all of the data in the collections. It's linear. One that we talk about is stacks. What's neat about a stack is, first of all, raise your hand if you have ever at any point in your life interacted with a stack of things. Wonderful, you're already experts. If I come along, and here's my stack of pancakes, and I add something to that stack, this is the top of the pancakes. If I add something to it, there's now something new on top. The top changed. If I remove something from that stack, I remove it from the top. I mean, you could be like, well, you could remove from the bottom. Now you're being ridiculous. Come on. You take from the top. If I took this one off, well, the top of the stack changed. The bottom remained unchanged. It's the top. The action is happening at the top. You add things to the top of the stack, you remove things from the top of the stack, right? You ever go to a buffet with those giant stacks of plates? Right. When the busboy comes out and puts a bunch of plates on, where do they put them? On top. When someone comes and takes a plate, where do they take it from? The top. Unless, like you said, they're psychotic. Don't do that. You take them from where they belong.
Or a magician.
Or a magician, yes, sure. All right. A queue. Have you ever at any point in your life lined up in anything?
Unfortunately.
Yes, of course you have. And if everyone's playing nice, there's a nice, simple system of your queue, of your line. There's the person at the front of the queue, and if you come along and you want to enter this queue, where do you go? Well, you go to the end. If you don't, leave this room, please. You're not welcome here. And if I'm like selling coffee and I say, next, who's going to come? This person, right? That's the idea of a queue. Now, how is it different than a stack? Well, with the stack, all of the action happened at one end, the top. You added things to the top, you removed things from the top. But with a queue, it's a little different. You add things at one end, but you remove them from the other end, right? A bag. Well, a bag is a very general idea, and so we might like to think of lists. Now, here's an example of an ordered list where the elements are ordered. I can add things to this list, but where I add them don't necessarily need to be at one end or the other end, and where I remove them from doesn't need to be at one end or another end. It's a little bit more general. Now, this is a constrained type of bag. It's an ordered one, meaning if I add something, it better get added where it belongs. Otherwise, it'll destroy the ordered property. But the idea is there, like I can add and remove to this thing, just like I could a stack, just like I could a queue. But the rules on how they are added and removed are different. I could create a more general list where the order doesn't matter, and I can say add it to wherever the hell I want. Just like how you would have in Python with the Python lists. Python lists are unordered bags. But then we have nonlinear collections, things like trees. Trees are great for representing hierarchies of things, where you can kind of like, yeah, just a hierarchy of things, really. So if you look at like the file system on your computer, you could say, okay, root directory, and then in that folder you have other folders, and in that folder you have subfolders, and so on, and so on, and so on. So this is a fairly general tree. And then finally we have graphs, which is like a generalization of, so by the way, trees are like a generalization of this like list idea. And then lists are trees can be generalized into like a graph, where you'll notice with trees, first of all, trees are nonlinear. Like if I'm here and I say, what comes after 40? You go, 51. Why? Because it's right there. What comes before 40? 29. Now here, if I say, you're at program files, what comes before program files? Well, the root, that one. What comes after? Well, this one, because it's alphabetical? Okay, sure, maybe, but I had to like think of an ordering. There's no like obvious ordering, right? It could be either of these. It's nonlinear. It branches out. I can't draw a straight line. We could come up with like patterns and rules on how like what comes after what, but I need to invent those after the fact, where like this, when I say what comes after, it's 51. And if you're like, yeah, but you had to decide, no, I didn't. It goes that way. It just is. By nature of how it's defined, it's part of like its definition. I had to create a new rule to define an ordering for this thing. And with graphs, it's even more complicated. What comes before Buffalo? I don't know. Halifax? Maybe, I don't know, right? Like it's not obvious. And graphs are great for representing how entities are related to one another. We call these things vertices. Each one's a vertex. Sometimes people call them nodes. Fine, fair enough. And the things that connect them are edges. And if things are touching, they're adjacent. That's a graph. Okay? You are going to be using graphs in assignment 2 and assignment 3 when you traverse mazes. Mazes are graphs, but we're not really exploring them as a concept. So you'll interact with them, but that's it. All right. Yeah. Now, abstraction. We've talked about this idea a lot. So hopefully by this stage, I'm kind of like beating a dead horse here. It's an important idea for problem solving. We do it all the time. It's often very valuable to separate the what from the how. Okay? I'm going to pick this up. What did I do? I picked it up. How? There's a lot that happened. I moved my arm. Yeah, but how'd you do that? I contracted my muscle. How'd you do that? Okay, right? We're separating these things because the what and the how are separate. Obviously, they are interconnected, but they are ultimately separate. So we abstract these ideas away from each other. We think of these things. And also, like we play that how game, we could play that game all the way down. So when I say what, pick up the marker. Why didn't I say draw something on the board, right? The what happened there, but like I'm discussing something at a higher level of abstraction. Okay, what we can do, how it's actually done. One may want to know what they have to do to drive a car, but I don't care how it works. I just need to be able to get in my car and drive. You knew how to append things, like you knew what to do to append things to a list in Python, but you didn't know how it did it. And that's fine. You didn't need to. So the above things that we talked about, those ADTs, they're just the what. I never said how you add anything to a stack. I described what it works, like what it does, and oh, we add things to the top. But how do we implement that in Java? We didn't talk about that. That's the how. The what and the how are separate. We'll pick up here tomorrow or whenever.